assign to it an address by dropping perpendicular lines onto x and y axis the way we did before. But instead, we will measure different characteristics. Namely, we'll measure the distance to the origin. Okay? And so we will call this r. We'll call this r. Now, if we just measure this, that's not going to give this point a unique address, because there are many points on the circle for which the distance to the origin is equal to r. In fact, we know precisely what this set is. This is the circle radius r. So there are way too many. What we're striving to do, on the other hand, is to find a way to assign to each point a unique address. So just measuring this by itself is not going to help us. We need additional information. And what gives us the additional information, which already uniquely determines the point, is the angle which this segment connecting the origin and our point makes with the x-axis. Let's call this angle theta. So now, you see, as I said, the set of all points which have distance r to the origin is the entire circle. But within that circle, there's only one point for which the angle is going to be a particular angle theta. So now we pin down this point in a unique way once we know these two numbers, r and theta. And these are called the polar coordinates. So there are several questions here. First of all, why do we need another coordinate system to begin with? Why can't we be satisfied with the original coordinate system, the Cartesian coordinate system? And the answer to this is that oftentimes, if you use the Cartesian coordinate system, you end up, for example, with various types of integrals, and these integrals are going to be single variable integrals like this for arc length or surface area. And sometimes they're just too hard. And even if you had an A plus on a 1B, you won't be able to get a number out of it. So even if you apply all the tricks, you're still unable to solve it. And so oftentimes you should try a different approach. And so oftentimes the same quantity can be expressed as a different type of integral, right? And the way to get to a different type of integral is to use a different coordinate system. And polar coordinate turns out to be very convenient in many cases. In many cases, it simplifies the answer. It simplifies the kind of integrals that we get. In fact, just a couple minutes ago, we discussed the question of rotating around a different line. You see, if we were to try to tackle this question by using just the x and y coordinates, we would get nowhere. It would be very difficult. What I mean to say is that suppose that we were asked to rotate a curve not around this axis but around this axis. It's a legitimate question. And so the answer to this question, the correct answer, is to realize that in fact, in addition to this coordinate system xy that I kind of draw without thinking on the board, has as much right to exist as a different coordinate system which is obtained by rotating this one by a small angle, in which we'll have two different axes, which I draw with pink chalk. So this one I call x prime, and this one I will call y prime. And once you translate it to this coordinate system, the question becomes exactly identical to the question we've discussed now, right? So this already makes you appreciate the fact that, first of all, there's not a unique coordinate system on the plane. So it's an illusion that there is a unique coordinate system, because the way I draw the horizontal line sort of parallel to the floor, right? But if I kind of tilt my body a little bit, then it will be like this, and also if you tilt the floor, right? So it's not a good reason. And so this tells you already there's a whole variety of coordinates you can get by rotating. All of those coordinate systems, though, have the same flavor. They have all Cartesian coordinate systems. They just rotated one from with respect to another by a certain angle. This one is sort of radically different. But this is already a good illustration that you should not be stuck with a particular coordinate system, that oftentimes to get an answer or to get a good solution or to get a better approach to your problem, it is advantageous to try a different coordinate system. So here we try something which is different. And the advantage of this is that equations of curves simplify, of certain curves simplify when you use this coordinate system. And of course, the curve for which the equation simplifies is the circle. Circle, I recall, can be parameterized using the traditional Cartesian coordinate system in the following way. We write x is cosine t, and y is sine t. That's not too bad, but see, we're using two trigonometric functions. By the way, this is for a circle of radius 1, but if you want a circle of radius r, let's call r capital to distinguish it from the other one. So circle of radius r. For example, circle of radius 5 would have x5 cosine t and y5 sine t. That's not too bad, but this is some trigonometric functions which are not elementary functions. On the other hand, in polar coordinate system, the equation, we could try to write equations for this curve as well, for the circle as well, using this new coordinate system, and the equation will simply be r equals r. So this is in polar coordinate system. So it's the same curve, the circle, but represented in two different coordinate systems. Here we use cosine and sine, here we use nothing. It's just r is equal to r capital. And keep in mind that here the small r and the big R play completely different roles. This r is one of the two polar coordinates. This is a coordinate like x or y. And this r is a number, because I'm asking you to write the equation for the circle of radius r. So for example, it's a number which could be equal to any number you want, like 5, for example. So in this case, the equation would read just r equals 5. So it's this type of equations that we get when looking at a circle from the point of view of polar coordinates. And surely this is a much simpler equation than this one. It doesn't involve sine or cosine. It doesn't involve any function of anything but constant function 5 or r in general. So that's a good illustration of the advantages of this coordinate system. The equations for some important curves like the circle simplify. And for this reason also various integrals that you get if you try to calculate the arc length, the surface area, and so on will also simplify. So that's the first point. Why do we need this coordinate system? It's useful in applications. The second question that we can ask is how to convert one coordinate system into another. Because let's say, okay, I convinced you that this is a very useful coordinate system, and suppose you are given a curve in the Cartesian coordinates, and you would like to translate this into the polar coordinate system. Or maybe conversely, you're given something in the polar coordinate system and translate back into Cartesian. So you need some tools, a kind of a dictionary, how to go from one coordinate system to the other. And that's actually done in a very straightforward way. You just have to express the coordinates x and y in terms of r and theta. And conversely, you have to express r and theta in terms of x and y. And once you do that, you have a dictionary which will enable you to go between the two coordinate systems very easily. So the dictionary is very simple. For this, we need to remember how the x and y coordinates are obtained. So this is x and this is y. And so now we see very clearly how to find what x and y are, because x and y are two sides of this triangle, in which one of the angles is 90 degrees, or pi over 2, the right angle, and another angle is theta. So for such a triangle, we can find the length of the sides by taking the length of the long side and multiplying by cosine and sine of theta. So therefore, we get these formulas. X is r cosine theta, and y is r sine theta, right? So that's it. What does it mean? It means that if you are given a point represented in polar coordinates by two numbers r and theta, you can find the xy coordinates of this point. For example, let's say theta is, in this example, let's look at this example. Let's say theta is pi over 4, 45 degrees, and r is 2. Okay, so this is 2, this is pi over 4. Right. So then you can ask what is x and y. So let's say 2 and pi over 4. You have to take 2 times cosine theta, and cosine theta is 1 over square root of 2. So it's going to be 2 over square root of 2, and likewise sine. In this case, sine and cosine are the same. So you end up with square root of 2, square root of 2. A very simple rule. So that's one way. What about the other way, if you want to go from xy coordinates to r theta coordinates? Well, in this case, we are given the two sides like this, and we need to find the length of the long side, and we also need to find the angle. And of course, we can do that because we can use Pythagoras theorem for the first one. So we get r is the square root of x squared plus y squared, and theta. So find theta, we have to find what we can find is the tangent of theta. The tangent of theta is going to be the ratio between this side and this side. So instead of writing what theta is, I'll just write the tangent of theta, and that's y over x. And once you know the tangent of theta, you should be able to find what theta is. So at this point, actually, we have to address one question which I kind of swept under the rug, which is what is the possible range for r and theta? What are the possible values for r and theta? So because if we want to use it as a bona fide coordinate system, we better know what are the possible values of its coordinates. So what are the possible values of r and theta? Before answering this, let's ask what are the possible values of x and y. It's also a legitimate question. We never asked it because it was sort of given that both x and y can take arbitrary values. When I say arbitrary, any real number, from minus infinity to plus infinity. For x, likewise for y. Because we assume that when we talk about the plane, we talk about the infinite plane, not just this blackboard, but the infinite plane, which is obtained by extending the blackboard in all possible directions, right? So x and y, the ranges for x and y are from minus infinity to plus infinity. Not so for the polar coordinates, right? For one thing, r was defined as a distance from the origin, and the distance is a positive number, or more precisely, it's a non-negative number. It could be 0 or positive. So r, in this definition, is greater than or equal to 0. Okay? What about theta? Theta is the angle, and we know that the angle goes from 0 to 2 pi. So it is wise to say that actually theta takes values between 0 and 2 pi, because if we start looking at theta, if we allow theta greater than 2 pi or less than 0, what will happen is that we'll sort of get double billing. We'll get different ways of representing the same point, right? Because we'll be the same point, for example, be pi over 4, but also 2 pi plus pi over 4, or 4 pi plus pi over 4, and so on. And when I was telling you about this coordinate system, one of the important properties that we wanted it to satisfy was that it gives us a unique address to a given point. So if we allow theta to take arbitrary real values, there will be infinitely many ways to represent the same point, because we could always then shift theta by 2 pi, and we'll get the same point. So that's why it's better to specify the range of theta as being from 0 to 2 pi. If we want to be pedantic, we should also realize that actually 2 pi is like 0. And so once you get to 2 pi, it's like you're back at 0. So you don't want to use the same angle twice, even if it's just one angle. So strictly speaking, it has to be from 0, greater than or equal to 0, but less than 2 pi. So this is how it's defined, how it should be defined, in order to get sort of unambiguous answer. And even then, we actually do have a small ambiguity. I kind of put it in brackets because it's really kind of a subtle point, which I'm not going to dwell on too much. But there is a small ambiguity. There is a small ambiguity. If r is equal to 0, we actually add the origin. And so theta becomes meaningless. We can't really say at what angle our point is with respect to the origin, because it is the origin. So if r is equal to 0, unfortunately my board doesn't look so good, so my 0 looks like theta now. I mean 0, really. If r is 0, then theta is not determined. So there's a subtle point that when I promised you that polar coordinate system gives you a unique address, assigns a unique address to each point, it's not strictly speaking true. It does assign a unique address to all points except the origin. For the origin, the address will be r equals 0, and theta could be anything. So there are too many addresses that you assign to that point. But because it's only one point, we're not really going to worry about it too much. So I'm just mentioning it to you so that you are not so startled by this when you realize it. It is a fact, but it's not going to be a big problem for us just because it's only one point, which is potentially problematic. Now, there is kind of a more important point here, which is that, in fact, we're going to allow in our calculations, we're going to allow more values for r and theta. We will allow, and this is sort of a technical thing. What I write here is how the polar coordinates are defined, strictly speaking, if we really want to define an unambiguous, say for this origin, unambiguous coordinate system. But in our calculations, it will be very convenient to have a certain rule and to allow points with negative r. So this is a rule of convenience, really. The rule of convenience is that if you have negative r, if r is negative, we will allow negative r with the following interpretation: negative values of r. Instead of explaining it in words, I'll just draw a picture because it's much easier to see that once than to hear it 10 times. And many of you probably already know that, those who have already tried to do the homework exercises for this section. The rule is like this, that if you have a point like this, r theta, then its mirror image, the point which is obtained on the other side of this line, will be called minus r theta minus r theta plus pi, right? So we'll follow this rule. That negative r, so if r is positive, you have this point. But then the point with negative r is going to be a point for which which lies on the opposite end of this line, which is negative to this point. Good, I'm glad. So okay, correct me. What should I write? Right, that's right, exactly. So if r is negative, then let's say you're given point minus 10 and then pi over 4. Okay, so where would we plot it? Okay, so if it was 10 pi over 4, clearly it would be somewhere here, right? But if it is, so the way I wrote it is not a good way. So let me just give an example using a particular values of r and theta. So this is a representation for r theta if r is positive. Let's put it this way. If r is positive, this is a representation. Okay, and if r is negative, then the representation, if r is negative, then it will be minus r theta plus 1, like this. So that's what I meant in this picture, but it was a little bit ambiguous. So in particular, if you have 10 pi over 4, it will be here. But minus 10 pi over 4 will be here. This is going to be the point pi over 4, which will be the same as 10 and 3 pi, pi plus pi over 4. Okay, it's like this. Yeah, when you write it, it's not clear when I say minus r, do I mean the original one or the minus of the negative one? I mean minus of the negative one. So it's not the same r as this one. If r is positive, r theta is just formed like this. And if r is negative, let's just do it like this. If r is negative, then you take, in other words, here you take the length r. And if r is negative, you take the length negative r, which will be now positive, and you take the angle, which is theta plus pi. I think it's clear now. Okay? So, yeah. You have to explain. You have to be careful when you try to explain. But we'll see now in a calculation, so you will see better what I'm talking about. All right. So let's see what we can do now with this coordinate system. Everything all right? Yeah. Are you getting tired? I guess Thursday afternoon. Are you all excited about the long weekend? Yeah. Well, we still have half an hour, but okay, let me take 2 minutes. But afterwards, you go. So let me let's take a 2-minute break just to relax a little bit. I want to tell you something. It doesn't mean that you should start. Oh, you still have to listen to me. This is my time. So I want to tell you about an article I read today in a Forbes magazine. Not that I read Forbes magazine regularly. Don't get the wrong idea. I saw it mentioned on the blog, and there's a link to this article. That's why I read it. It's available electronically, and it's a very interesting article about string theory and about the controversy about string theory. And I'm interested in this because it's not very far from my research interests, which involve quantum field theory and mathematical aspects of quantum field theory. But I like this article because I remember on the first day when I said that people think of mathematics and science as a kind of something which has been written in stone and hasn't changed in many years, which in fact is not true. And this article is a very good illustration, and I even copied a quote. I copied a sentence from this article from the very beginning, which I think is written very nicely. So he writes, the author writes, lay people tend to regard science as a lofty temple inhabited by serene, spoke-like wise men. Working scientists, though, will tell you, it's more like a stock market, full of fads and fashions, booms and busts. So I like this analogy, not so much, I don't like it if it's not, the meaning is not to say that it's as speculative as the stock market, but I think it's a good illustration of the fact that it is really a live organism, which is constantly changing, like the stock market. So in that sense, I think it's a good analogy, because it's Forbes magazine, of course, they use that analogy. That makes a lot of sense. Just like stock market goes up and down, and things change. Likewise, in science and mathematics and physics, things also go up and down, and certain things become fashionable, and then they fall out of fashion. And at the end of the day, it's the fundamentals, which you really care about, not the speculation, and not sort of the all the artificial things. So I think that it's really cool, and I really like this analogy with the stock market. And I really recommend this article. It's very short, and it sort of talks about one of the most interesting ideas of the last maybe 30 years in science, string theory. So I'm going to put a link to this article on the BSpace, on our BSpace page. And if you come across any article about math or science which you would like to share with other students, please send me the link, and I'll post it as well. Okay? All right. Now back to the boring stuff. I'm kidding. It's actually it's not boring at all. So, and maybe another day we'll take a break. We'll take a small break, and I'll tell you a little bit about what string theory really is. Okay. But now let's go back to polar coordinates. All right. So let's look at various curves and at how to represent those curves using polar coordinates. So we already talked about the circle. Circle of radius r is represented by the equation r equals r, where r is one of the two polar coordinates, and this is the radius. So here's another example. A line passing through the origin with angle theta to the x-axis. Also given by a very simple equation, namely now theta is a constant. Angle theta 0, say. What I mean to say is